Welcome back to Think Cosmos, where we ponder the universe's deepest secrets and wonders. In the center of a distant galaxy, a black hole is having a violent tantrum. And it's not the quiet, dignified kind of outburst we once assumed. No, this supermassive black hole is firing off salvos of gas like cosmic bullets, blasting them outward at a significant fraction of the speed of light. It's a scene so dramatic and energetic that it challenges what we thought we knew about how black holes interact with their galaxies. Let's set the stage. When you imagine a black hole, you might picture a monstrous dark void silently gobbling up anything that ventures too close. And that's true. Black holes are voracious eaters. But they can also blow matter back out in the form of intense winds or jets. Think of it like an exceedingly messy eater that also spits out some of its food. These outflows, fast winds of radiation-charged gas, are crucial because they're one of the main ways a black hole communicates with its galaxy. They can push on interstellar gas, potentially triggering or halting star formation, and effectively link the fate of the black hole with the evolution of its whole host galaxy. For years, scientists believed these black hole winds were relatively steady flows, like a continuous breeze, albeit an incredibly fast one. In our models, we often treated them as smooth streams of particles streaming out from the disk of material swirling around the black hole. But recent observations from a cutting-edge X-ray telescope have completely upended that picture. Instead of a steady hurricane, it seems we're dealing with a chaotic Tommy gun, firing sporadic bullets of gas. This discovery came from an international team using XRISM, pronounced XRISM, a new X-ray observatory developed by Japan in collaboration with NASA and others. XRISM has the special ability to precisely measure the velocities of extremely hot ionized gases in space. When the team pointed it at a known quasar, basically an active supermassive black hole that's feasting on material and glowing brightly, what they found was astonishing. They observed a quasar called PDS 456, one of the most luminous and well-studied black hole systems out there. PDS 456 was already famous among astronomers for having powerful winds, sometimes called ultra-fast outflows, rushing outwards. But XRISM's data revealed that these winds aren't one monolithic gust. In fact, they detected at least 5 distinct components. You can think of them as 5 separate clumps or shells of gas, each hurtling out at a slightly different speed. And we're not talking about gentle breezes here. These were whipping out at about 20% to 30% of the speed of light. That's on the order of tens of thousands of kilometers per second. Wow. Each clump was moving at a different velocity, which is a dead giveaway that the wind is not uniform. It's a bit like hearing a bunch of sonic booms instead of a continuous roar. It tells you that something is coming in bursts. One analogy could be a geyser. It could be a geyser. Imagine Old Faithful in Yellowstone, which doesn't flow constantly, but rather builds up pressure, and then releases in dramatic bursts. The black hole's accretion disk, the maelstrom of superheated gas spiraling into the black hole, might similarly be episodically ejecting chunks of gas. Another analogy. Think of a battlefield cannon firing grape shot. A whole bunch of projectiles sprayed out in sequence, rather than a single continuous beam. However you picture it, it's dynamic, clumpy, and surprisingly structured. This bullet-like wind was a revelation, because it tells us the environment near that black hole is far more structured than a simple wind model would suggest. One possible scenario is that the area around the black hole has patches or gaps, perhaps due to magnetic fields or disk instabilities, which cause the outflowing gas to channel into discrete funnels or blobs and launch outwards periodically. Another idea is that the wind might start off somewhat continuous, But as it plows through the surrounding medium, the gas and dust around the black hole, it breaks into fragments, kind of like how a flowing water hose spray can break into droplets if it hits the air. Now, the observation alone is fascinating, but what really has scientists buzzing are the implications of these powerful gas bullets. The energy carried by these outflowing chunks turned out to be immense. The team found it was more than 1,000 times greater than the energy in normal galaxy-scale winds, like the winds emanating from star-forming regions or smaller black holes. These quasar winds are basically supercharged. When you concentrate energy into bullets instead of a diffuse flow, each bullet can pack a tremendous punch. And when those bullets slam into the galaxy's interstellar medium, they can deliver that energy in localized, potentially devastating blows. We're talking the ability to shock heat gas, push clouds around, and possibly suppress star formation in the galaxy by clearing out or heating up the very gas that would otherwise cool and collapse into new stars. This ties into a long-standing puzzle in astrophysics. How do galaxies and their central black holes co-evolve? Observations have shown a correlation between the mass of a galaxy's central black hole and certain properties of the galaxy, like the mass of the galaxy's central bulge of stars. It's like big galaxies have big black holes. Small galaxies have small black holes, hinting that somehow the growth of the black hole and the growth of the galaxy are linked. But black holes are tiny compared to galaxies. On relative scale, a black hole is like a grain of sand in a cathedral-sized. So how does the black hole exert influence across tens of thousands of light years? Winds and jets are the answer. These outflows can transfer energy from the vicinity of the black hole out to the galaxy at large, a process we call feedback. Yet, until now, we were fuzzy on the details of how that feedback actually worked. Was it continuous? Intermittent? And how strong? The discovery of clumpy, high-energy bullet winds suggests that feedback might be more violent and intermittent than we assumed. Instead of gently puffing out the equivalent of a cosmic breeze to nudge star-forming clouds, the black hole might be intermittently punching the galaxy with energy. Imagine a series of super-powerful shockwaves passing through the galaxy's core like repeated cosmic punches. This could explain why some galaxies have their star formation abruptly quenched. The black hole essentially blows out the candle, snuffing out the gas that would fuel new stars. Conversely, in some cases, these shock waves might also compress gas in front of them, possibly triggering star formation in some zones, even as they quench it in others. The net effect is complex, but it clearly shows the black hole can dominate the narrative of what happens in the central region of its galaxy. Another major implication is for our theoretical models. Many earlier computer simulations of galaxy evolution, by necessity, had to simplify the behavior of black hole winds. They often treated them as steady inputs of energy. With this new insight, modelers might need to incorporate a bursty feedback mode, like a sputtering engine rather than a smooth one, and that could change the outcomes of those simulations. It might produce galaxies that look more like the ones we actually observe. For instance, explaining odd shell-like gas structures or sudden halts in star formation observed in some systems. Now, how did XRISM manage to figure this out? The key was spectroscopy, essentially breaking down X-ray light into a spectrum, which can show Doppler shifts. Doppler shifts are the telltale stretching or squeezing of light wavelengths when something is moving toward or away from you. Think of the siren of an ambulance changing pitch as it passes by. That's the Doppler effect with sound. With light, if gas is moving toward us, its spectral lines shift to slightly shorter, bluer wavelengths. If it's moving away, they shift to longer, redder wavelengths. XRISM's instruments are so precise they could detect multiple different shifts in the quasars, X-ray, spectral lines, corresponding to gas moving at different speeds. That's how they disentangled the 5 distinct components of the wind. It's worth noting that catching such detailed structure is not easy. This is like a first-of-its-kind observation. XRISM, launched relatively recently, is a successor to previous X-ray missions and has advanced detectors that can measure slight energy differences in incoming X-ray photons. Without this tech, the multiple bullets might have just blurred together into what looked like one broad smear, and we wouldn't know any better. It's a triumph not only for astrophysics but also for engineering. Building an eye sharp enough to see the fine details in the furious fireworks of a quasar. What's also poetic about this finding is that it strengthens the narrative of an ecosystem at the galaxy's center. We often isolate phenomena. Black hole here, stars there, gas over here. But really, they're deeply interconnected. The black hole's diet, how much matter it accretes, determines how much energy it can spit back out. That energy output then can blow out surrounding gas, which in turn might starve the black hole of further food. Essentially, a self-regulating mechanism. If the black hole gets too gung-ho and starts devouring too fast, it blows out so much energy that it pushes the remaining dinner away. A cosmic stop. I'm full moment. Then things calm down. The black hole quiets until gravity can pull new gas in, and the cycle might start again. These bullet winds fit nicely into that kind of cyclic feedback loop idea. On and off phases of activity. For the scientists involved, this must have been an exhilarating discovery. Imagine being the first to lay eyes on evidence that, this wind is not single but multiple discrete blasts. It's a reminder that nature often has granularity, like how atoms were once thought to be the smallest things. And then we discovered protons, neutrons, electrons, and then even those have quarks, etc. Likewise, a wind sounds singular and uniform. But zoom in with better tools, and you find a detailed structure within. Now, you might wonder, does this phenomenon affect us here in the Milky Way? Well, our galaxy's central black hole, Sagittarius ARC-EE, is much quieter and smaller scale than a quasar like PD's 456. We don't have such extreme winds at the moment, thankfully. But in the distant past, it might have had episodes of feast and feedback too. There's some evidence in gamma-ray bubbles and other features that suggest our black hole burped energy in the past. However, PD's 456 is sort of an ideal specimen because it's unusually powerful, giving us a clear signal to study. It's likely not alone. Other quasars probably also have bullet winds, and astronomers will no doubt use XRISM and future X-ray telescopes to check more of them. There's also a natural human excitement in this. Black holes already capture our imagination, and this just adds another layer of coolness and craziness to them. We used to say nothing can escape a black hole once it's past the event horizon, which is true, but before stuff falls in, it can heat up, and some of it can be flung out at high speed. We are now seeing that this expulsion can be extremely energetic and structured. It's like learning that a predator not only eats its prey, but also mightily roars and reshapes the environment around it in the process. Let's also appreciate that this finding was published in Nature, which is one of the top scientific journals, meaning the community recognizes this as a significant breakthrough. For the field of galaxy evolution studies, it's a highlight of the year. And for the XRISM mission, it's a flag in the ground, showing that the telescope is delivering on its promise. Stepping back, what does this mean for our broader understanding of the universe? It underscores that the big things and small things are connected. A supermassive black hole, small in size, though huge in mass, influences an entire galaxy, huge in size, and it does so not silently, but with forceful, episodic outbursts. It's almost a bit like a heartbeat or breathing of a galaxy. Intake, matter accretion, and outflow, winds in a rhythmic, if irregular fashion. Over the lifespan of a galaxy, These cycles could happen many times. It also leaves us with new questions. Why 5 distinct components? Is that just what we happen to catch, or is there some physics that tends to produce around 5 bursts? Could it be like a series of shocks that naturally space themselves out? Or perhaps the disk is orbiting, and as different regions of the disk line up, they produce separate streams. We're not entirely sure yet. This is just the first observation of its kind, and it will spur both more observations and theoretical work to explain the detailed structure. Another thought. If an alien civilization were positioned in the path of one of these bullets, boy, would they know something weird was up. It would be an intense flash of X-rays and energy from their galactic core, possibly affecting their planetary system. It's a reminder that the universe can be a violent place, and even at tens of thousands of light years away, a quasar's temper tantrum can send ripples of disruption. As we end this tale of cosmic weaponry, picture the core of PD's 456 now, with this new lens, not as a gentle beacon, but as a powerhouse that occasionally goes shotgun mode. It's beautiful in a way, a beautiful violence that shapes the cosmos. And it makes one wonder, what other surprises are lurking in the hearts of distant galaxies? We only found this because we had a new tool and looked carefully. The universe tends to reward such curiosity with deeper and more unexpected wonders. The next time you think of a black hole, don't just think of an all-consuming darkness. Imagine it also as a force that can shed energy in furious, breathtaking bursts, sculpting the very galaxy that nurtures it. With each new discovery like this, our picture of the cosmic ballet changes. What do you think might be the next revelation about how black holes influence their cosmic homes?